Good evening, all. Welcome to Unacademy, largest online e-learning platform, Unacademy Semester Exams. We are dealing with Control System Engineering crash course, and today's topic is RH criteria and Rootlocus. For this, let me tell you, I am Vice Shravan Kumar, having 7+ years of experience in teaching, mentored more than 5K students for GATE and engineering services, and cracked GATE. And before getting into today's topic, let me explain you the procedure of downloading and getting subscription to Unacademy. Unacademy learning app, type it in Play Store, and you'll get this step 2 installation process. And in step 3, if you are opting for Gate and Engineering Services, click on this. You can subscribe to Plus or Iconic and click on this Get Subscription. You have both Plus and Iconic. As I tell you, Iconic has a separate mentor dedicated for your preparation. You can use my code as YSK10 to get maximum discount. And you have various types of payment options: debit card, credit card, EMI, UPI, wallets, and net banking. You can use any of these payment methods to make your payments. So today's topic are stability, RH criteria, root locus. I welcome you all. Rishikesh, hi, hi sir, hi. Arvind Gupta, good evening sir, good evening Arvind Gupta. Please share with your friends and so that they will also get benefited out of this. Request you all to share this. भेज दो सब लोगों को, and everyone will get benefited of the out of this. These are two important topics of control systems: RH criteria and root locus, wherein you'll find the stability of a given system. Chandrakiran, good evening sir, good evening Chandrakiran. Harita, good evening sir, good evening Harita, and thank you for joining. I want everyone to join this. Let's see for a while, and people start joining again. So let's start with what is stability. Stability is defined as for a bounded output, you get a bounded output for a given bounded input, or else for a given bounded input, if the output is also bounded, then the system is said to be stable. And there are other stability also. One is if the system output is stable for all variations of its parameters. This is called as absolute stability or absolute stable system. If system output is stable for all variations of its parameters, it is an absolute stable system. If system output is stable for limited variation of its parameters, then it is called as a marginally stable system. I'll give you some examples. Good evening, sir. Good evening, Shiva. So, a system is said to be stable if its input is bounded and if the output is bounded for a given input. And an absolute system is one whose output is stable for all the variations of its parameters. And a marginally stable system is one if the system output is stable for a limited variation of its parameters. Now, let me tell you about impulse response. Then we'll see. Consider f of s as the transfer function, c of s by r of s. Now you can write from this c of s is equal to f of s into r of s. Now what is r of s? R of S is the input in Laplace domain. If input is impulse, you can say R of S, that is R of t is delta of t and R of S is 1. Now if you find the response of this, if you apply Laplace inverse, it is C of t is equal to Laplace inverse of f of s into R of s, where R of s is 1. You can write Laplace inverse of f of s, or you can also write it as f of t. You can say that impulse response is, this is the impulse response. Impulse response is inverse Laplace of transfer function. That's what it is. If you see here, this is the impulse response is the Laplace inverse Laplace transform of the f of s. This is impulse response. Now let me tell you some examples of stable, absolutely stable, marginally stable and condition marginally stable systems. Sorry. Now if you consider 1 by s plus a as your transfer function, now response of this would be, if you apply Laplace inverse of 1 by s plus a is, good evening, e power minus at. E power minus at and represent it as, this is the response. If this is f of s, let us say this is f of s or f of t with respect to t. Now this will be a stable system, absolutely stable, absolutely stable one. If we consider other one, f of s is equal to 1 by s square plus a square. I'm sorry, is s square plus a square. Now write the Laplace inverse of this. What is the Laplace inverse of this or time domain function? It is 1 by s square plus a square. Laplace inverse. Chandrasekhar Reddy. Good evening, sir. Good evening, Chandrasekhar Reddy. First, try to write the inverse Laplace transform, the given transfer function 1 by s square plus a square. This will be Laplace inverse of 1 by s square plus a square. You know Laplace inverse of, I'll just write Laplace inverse formula first. Laplace of sine at is equal to a by s square plus a square. You should know Laplace inverse formula. In order to know that, Karthik Jilla, good evening, sir. Good evening, Karthik Jilla. So, what is the Laplace inverse of this? The Laplace inverse of this would be sine at. Now, you don't have a here. If it is a by s square plus a square, it is sine at. So, this is this one. Output is sinusoidal function. So, that means it is a marginally stable system. It is a marginally stable system. Now, let's write other one. Consider third part. So, third one is 1 by s plus a whole square. What is this 1 by s plus a whole square? Mohammad Rahiz. Good evening, sir. Good evening. It is the Laplace inverse of this is t into e power minus at. The response will be something like this. If you apply response to this, this is t multiplied by e power minus at. So this is t and this is f of t. This is also a absolutely stable system. Absolute stable system. Now let us consider fourth one, 1 by s plus a whole square plus fourth one b square. What is the Laplace inverse to this if you write? Laplace inverse is, you need to know the Laplace transform of the given function first. So first shifting theorem, it is Laplace of e power at into f of t is f of s at s is equal to s minus a, or you can also write it as f of s minus a. The Laplace inverse of this would be Laplace inverse of this is e power at sin bt. Is e power at into sin bt. You need to have a good knowledge of Laplace inverse and Laplace transform, else you'll not be able to understand this. So s plus a whole square e power at into sin bt, you'll get function like this with a decreasing oscillations. Exponential multiplied by a sinusoidal. Exponential is something like this, e power minus at into. So this is also a absolute stable system. I'll just review what we have done. Arvind Gupta, yes sir. Good evening. Let's see. First one, it is f of s is equal to 1 by s plus a. Its Laplace inverse would be e power minus at. E power minus at is a decreasing exponential function, which is a stable system again. Now, if you are looking at the second one, f of s is equal to a by s square plus a square. Its Laplace inverse would be sin at, which is a continuously oscillating function. Therefore, it is a marginally stable system rather than an absolute stable system. Coming to the third one, a 1 by f of s is 1 by s plus a whole square. It is t into e power minus at because Laplace transform, you need to know Laplace of t power n is equal to n factorial by s power n plus 1. So, and apply first shifting theorem to this, you'll get s power at s is equal to s minus a. So you'll get t into e power minus at, which is t is the linear function and e power minus at is a decreasing function. This would also be an absolute stable system. Coming to fourth one, 1 by s plus a whole square plus b square. Using first shifting theorem, if you write its Laplace inverse, it is e power minus at into sin bt, which is the multiplication of exponential and sinusoidal, will give you a decreasing oscillation. This is also an underdamped response. It is also an absolute stable system. There are other forms also available. I'll just give you those also. Now, if you see what are the things that we have seen, 1 by s plus a, 1 a by s square plus a square, 1 by s plus a whole square, 1 by s plus a whole square plus b square. Here you have seen this is an absolute stable system, it's a marginally stable system, this is an absolute stable system, this is an absolute stable system. Hope we'll go with the next one, fifth one, if you are clear with this. 1, 2, 3 and 4. Now if you look at the fifth one, sorry, the fifth one would be if the transfer function f of s is equal to 1 by s. If it is 1 by s, its Laplace inverse will be 1. Laplace inverse of f of s will be 1. So that will give you this sort of function, which is a straight line or a constant value for f of t versus t. So this will also be a marginally stable system. this will also be a marginally stable system or conditionally stable system. Now coming to the sixth one, if you take up the sixth one, if the f of s is equal to 1 by s square, what is f of s is equal to 1 by s square? Laplace inverse of this will be 1 by s square. Laplace inverse means you have repeated roots at the origin. First thing that you have to understand from this is it is s square implies s is equal to 0, s is equal to 0, repeated roots at origin. I'll tell you about these roots at different places. This is one root at origin. I'll write these things again. So this is 1 by s square. 1 by s square f of s is equal to 1 by s square is a transfer function. What would be its Laplace inverse? It is f of t is equal to t. So if you plot it, you plot this, it's a t, the ramp function. It is not a bounded input, bounded output. You can say this is an unstable system. We'll write it with the other mark, other color. This is an unstable system. I just want to give you an idea of which are stable systems and which are not stable systems. Ishita Gauravam, sorry if I'm wrong. Good evening, sir. Good evening. Good evening, Rishita. So this is one unstable system. Till now we have seen this was a stable system. Second one was a marginally stable system. And the third one is absolutely stable system again. So this is also an absolute stable system. And this was a marginally stable system 1 by s. And 1 by s square is an unstable system. We'll also look at some other terms. The seventh one, if you are taking up the seventh one, seventh example, so it is 1 by s square plus a square this we have seen 1 by s square plus a square, that was a sinusoidal. Now if you take 1 by s square plus a square whole square, 1 by s square plus a square whole square, if you are taking Laplace inverse of it, you'll get a function which has a response of increased oscillations, and this is also an unstable system. This is also an unstable system. Likewise, you have many other systems which are stable, unstable, marginally stable, depending upon the given transfer function. This is stable system, marginally stable system, absolutely stable system, absolutely stable system, marginally stable system, unstable system. Let's look at the roots, then I'll tell you the next eighth one also, then we'll see what are the roots of each. Now if you look at this, where are the roots of this transfer function? First let us look at this. So we said this is a stable function. We'll comment on the roots. Where are the roots when they are stable? Now if you look at this root, root is a denominator, pole. Where is a pole? So s is equal to minus a. Now if you plot it in s plane, if you try to plot this in s plane, let us consider this as an s plane. If this is an s plane, if this is s plane, s is equal to sigma plus j omega. So this is the real axis, this is the imaginary axis. S is equal to minus A will lie somewhere on the negative real axis. So whenever you have a root on the negative real axis, we can say that the system is a stable system. Now if you take up the second one, denominator, if you take s square plus a square is equal to 0 as a characteristic equation, so s square is equal to minus a square, s is equal to plus or minus ja. That means if you plot the same on, if you plot the same marginally stable system, if we try to plot it on an s plane, let's consider this as an s plane. So this is an s plane. So you have roots on, one is plus ja, other one is minus ja. You have a root on j omega axis. This is j omega axis, this is sigma. So if you have roots on the imaginary axis, j omega is called as an imaginary axis, then we can say the system is a marginally stable system. Hope this is clear. I'll just try to repeat once again. We have taken the denominator of this function to find the poles or the roots of the equation. So we can make it equal to 0, that is s plus a equal to 0 will give us s is equal to minus a. So s is equal to minus a, if you plot it, the pole is on the left half of s plane. We can say if the pole is on the left half of the s plane, the system is a stable system. Now we have taken the second one, we have found its roots. It has an imaginary roots on imaginary axis. If the roots are on imaginary axis, we can say that the system is a marginally stable system. Coming to the next one, now if you take this s plus a whole square, now same way if you take s plus a is equal to 0, s is equal to minus a, s is equal to minus s plus a into s plus a is equal to 0. Now if you try to, we'll try to plot this once again. It's an absolute stable system as I have told you. So this is a stable system. Now let us consider the s plane locations. Now if this is the s plane, what are the two roots? One is minus a, other one is also minus a. If you have, this is minus a, here you have again a minus a, so repeated roots, but where are they lying? They are lying on the left half of s plane. This plane is called as an s plane because this is real axis, this is j omega axis. So if the roots, repeated roots on the left half of s plane, then it is also a stable system. Now consider next one, fourth one. If you are considering, this is also an absolute stable system, we have told. So this is also a stable system. Now let us try to plot its s plane, plot the poles on the s plane. Now consider this. This is an s plane with sigma and j omega. What are the roots of this? S plus a whole square plus b square. Let us write it as s square plus a square plus 2sa plus b square. If you find the roots of this, you'll get complex conjugate roots which are on the left half of s plane. So whenever you have roots on the left half of s plane, then the system is stable. That is what we have deduced from all this. Now let's go with the fifth and sixth, seventh one also. Let's look at this fifth one. It's a marginally stable system, we have told, and let's try to plot it. I'll just draw it very little. अभी देख लो, what is this? S is equal to 0 is one root. So s is equal to 0 is the root. So the pole is at the origin. If the pole is at the origin, it can be it can be a stable or unstable system. So it is a marginally stable system. So let's look at s square. What is s square? Indicates s square is equal to 0. If you find roots, s is equal to 0 comma 0, that is repeated roots at the origin. Now let's try to plot it on s plane. So this is the s plane, and if you plot this, as I've been telling you, this is real axis, this is imaginary axis, have repeated poles. Whenever you have repeated poles, repeated poles at the origin, You can say it is an unstable system directly because its response is a ramp, which is not a bounded output. Likewise, you can also, maybe this is not visible for you, I'll just cut it and show you like this. Yeah, if you look at this, just show you this part first. Because there are repeated roots here, this is repeated roots or at the origin, so this is an unstable system. All right. Yeah, it's coming to this s square plus a square whole square. Now if you write s square plus a square whole square is equal to 0, you'll write it as s square plus a square is equal to 0 and s square plus a square is equal to 0 because you have to write twice. So you'll get 1 s square plus a square is equal to 0, other s square plus a square is equal to 0. So s is equal to plus or minus ja, s is equal to plus or minus ja. These are the roots. That means here the important point is if you take up the s plane, if you take up the s plane, this is j omega axis, this is sigma axis. Where are the roots? We have repeated roots on the imaginary axis. Plus ja, this will be plus ja and this is minus ja, and the roots are repeated. Here it is double, here it is double. Now if the roots are repeated, roots are repeated on j omega axis, then it is confirmed that it is an unstable system. Hope this is clear for you. So let us take other part of eighth one. I'll show you directly this eighth one. Now eighth one, let me take the example as f of s is equal to 1 by s minus a. If it is s minus a, what is its Laplace transform first? Is e power at sat, an exponentially increasing function. If you try to draw it, if you try to draw this, it is an exponentially increasing function. And also if you find the root of this s is equal to a, and if you try to plot it on s plane, if you try to plot this on s plane, this is sigma and this is j omega axis. S is equal to a is a positive number which is on the positive real axis. So whenever you have root on right half of s plane, you can say because this is an increasing function, it is f of t versus t, it is not a bounded one, so this is an unstable system. So you can say whenever the root is on right half of the s plane, then the system is unstable because it is giving me a response like this. You can also take f of s is equal to 1 by s minus a whole square. We will have s is equal to a and s is equal to a, two roots, and the response will be, so you'll have to do this, and I'll plot the s plane locations also. Maybe this s plane locations are not visible to you, just move a little this side. Yeah, hope this is bit clear for you now. Whenever you have repeated roots on the RHS, directly you can say that these are the repeated roots. So these are the repeated roots on the right half of the S plane. You can say that system is also an unstable system. If you try to find the Laplace transform to this 1 by s minus a whole square, this what is Laplace inverse? Laplace of, try to take this to the next slide. We'll take this to the next slide. Now let us take this. What is the Laplace of t into f of t is e power n by s plus a into, we'll also do this, we'll also do in the other way. So we can write it as 1 by s plus a whole square. 1 by s minus a Laplace inverse is e power at. Now what is Laplace of t power n? T power n is equal to n factorial by s power n plus 1. So Laplace of t is 1 factorial by s square. So Laplace of t into e power at into t. If you write Laplace of e power at into t, what can you write it as? 1 by s minus a whole square. So the Laplace inverse of this will be e power at into. Hope this is clear for you now. Arvind Gupta, thank you, sir. Best explanation. Rakesh, nice explanation, sir. Thank you. Thank you, Rakesh. Hope you are able to understand these concepts. Now, if you try to plot this, sorry, if you try to plot this response, you get t into e power at, a response something like this, which is again, this is t into e power minus at, t into e power plus at. It's an increasing exponential function, which is an unstable system. Now, if you plot it on a omega axis or s plane, so this will give you what are the roots of this s minus a whole square. So s minus a whole square are the roots repeated on the right half of s plane. Whenever you have roots on the right half of the s plane, system is unstable system. Finally, I can conclude that I'll just give you, if roots are on left half of s plane, then system is stable system. And if roots are on right half of s plane, then given system is an unstable system. So these are the conclusions of the last previous slides. You can also have, if the roots if the roots on, if there are roots on the imaginary axis, then it is a marginally stable system. If the roots are repeated on the imaginary axis, it is an unstable system. If you have a root at the origin, it is a marginally stable system. Likewise, you can have, but these are the main conclusions that you have to remember. If the roots of the given transfer function or given transfer function are on the left half of the s plane, then the system is a stable system. If the roots are on the right half of the s plane, then the system is an unstable system. With this idea, we will try to learn what is RH criteria. It was all about stability. I think you are clear with this stability concept that I have told you. This part we are done with. We are moving on to RH criteria. Concepts with that we have derived at will be useful in Routh-Hurwitz criteria. I'm sorry. These are the conclusions. If the roots are on the left half of the s plane, then the system is a stable system. If the roots are on the right half of the s plane, then the system is an unstable system. At least one root is on the right half of s plane, then the system is an unstable system. Hope you are clear with this. I'm moving on to the next one. Now we are learning what is RH criteria. This RH criteria is useful in determining whether the given system is stable or not. It does not give us any information of exact location of poles. That is one of the disadvantage of this. Because we had, let's say we have s plus 4 is equal to 0. You can directly tell s is equal to minus 4 is a root which is on the left half of s plane, and the system is a stable system if the denominator is 1 s plus 4. Now if you have, let's say, s square plus 2s plus 4 is equal to 0, you can directly find s1 is equal to s2 is equal to and comment on the stability of the system. If the given transfer function contains, let's say, s power 5 plus 5s square plus 6s cube plus, sorry, I'm sorry. If it has something like this, you can also take that s power 5 plus 7 s power 4 plus 3 s cube plus 2s square plus 8s plus 20 is equal to 0. It becomes very difficult for us to find the roots of this and comment on the stability of the system. This will become difficult. So in order to solve such very high polynomial characteristics equations, we are using this Rout-Hurwitz criteria, wherein he had told about Routh's array and a procedure that we will look with an example that will be very easy to understand if we are looking at this particular RH criteria with an example. There are some uh, difficulties while we are doing this, and there are some solutions and rules how to overcome those difficulties. I think this is an very important topic for semester exams. One question will definitely be given on this Routh-Hurwitz criteria always in all the semester exam question papers. In most of the semester exam question papers of all the universities throughout India, there will always be a question, most of the times at least, there will always be a question on this RH criteria. Even in your GATE examination, at least alternative year, you'll get one question on this Routh-Hurwitz criteria. We will look at this RH criteria step by step. I'll just give you one example first. We'll pick up with one example and what is Routh's criteria exactly and how we can comment on the stability of this given system. So in this Routh's criteria, we need to consider characteristic equation. You need to take 1 plus g of s into h of s is equal to 0 and follow the procedure Routh's array, and then we need to comment on the stability of the system. Let us take an example first. I'll start with an example of, say, I'll have to take one example from Nagurkani textbook, s power 4 plus 8 s cube plus, take one example, 8 s cube plus 18 s square plus 16s plus 5 is equal to 0, and we are asked to find the number of roots on left half of S plane and the right half of S plane, or question can also be asked something like this: comment on stability of a system whose characteristic equation is given. Now in this we need to follow steps. Steps will be something like this. I'll just give you. First you need to make an array. Let's make an array like this. First you need to draw an array and start with the highest polynomial given. highest polynomial given is s power 4 here. So start writing in the column row wise s power 4, s cube, s square, s power 1 and s power 0. That's how you need to write. Listen clearly, this is a helpful session for you. RH criteria is one important problem that is being asked every time in your examinations. So when you write s power 4, because this is an even power, consider all the coefficients of even power. This is one coefficient here. This is the second even number, so even polynomial. So the coefficient here is 18 and s power 0, is the coefficient here is 5. So write those 1, 18, yeah, write 1, 18 and 5 in the row of s power 4. Next, write odd polynomial coefficients 8, 16. You don't have the other one, write it as 0 or just you can leave it. Write 8, 16, just leave it, or you can also write a 0 here. And how to find s square? Always remember, first two rows must be, first two rows has to be completed from when characteristic equation. First two must be completed with the when characteristic equation, first two rows. And from the third row, you will have to calculate from the given two rows. This is a procedure of RH criteria. So third row will have to be calculated from the above two rows. So that I'll tell you how to calculate that. Let us say you have A, B, C and D. This is s power 4 and this is s cube. Now how to calculate s square is, now let us take, you need to do something like this: E into C minus A into D by C. This is the expression that you need to take. Find the first column element. In order to find the second column element, let us say you have need to shift this B and D the next column. You need to consider this B here and D here. You need not shift the numbers, you need to consider them here, numbers which are here, and use the same expression and find the next number. Likewise, you'll find the rest of the numbers, even the rest of the elements in the row, and you'll complete the routes array. I'll just repeat it once again. Once I solve this, I'll try to repeat this. Now, so this will be, in my case, this is A, this is B, this is C, and this is D. Sorry. What would be this element is 18 into 8 minus 16 into 1 by 8 will be this element. You can also do one more thing here. If you are not interested to see in this row, you have 8 and 16, you can replace them by other numbers also. I'll tell you to make it very easy, you can also do these things. See, instead of taking, you can scale it by 8, so it is 1 and this is 2. If you are confused, don't scale it, just take it as 18 and 6, 8 and 16, doesn't matter. But if you want to make it very easy and this row can be scaled by a factor of 8, you can make it 1 and 2 and do the same thing. Now maybe you'll get confused, so I'm not doing that. Let us take 8 and 16. So this is C, and I'll write it with blue. This is C and this is D. So BC into AD is C. So 18 into 8 minus 16 into 1 by 8. So this value, so 18 into 8, 8 8s are 64, you'll get it. So 64 and 8's 144 minus 16 by 8. You can calculate this, and so what is this value? 18 into 8 minus 16 into 1 by 8. I think you can tell this number. 18 into 8 minus 16 into 1 by 8. At least one of you can tell me what is the value of this. 18 into 8 minus 16 into 1 by 8. 144 minus 16. What is 144 minus 16 by 8? It is 128 by 8. So it is 16 again. So here the value you have to write is 16. Coming to the next one, whenever you want to find the next row, just shift this B and D and write it here B and D. Because you don't have anything here, take a 0. So what to write this? How to write this? Same A into, sorry, now C into B, B into C minus A into D by C. So that is, what is that value? 8 into 5 minus 1 into 0 by 8 again. So it is 5. So this value is 5. I'll try to repeat this once again. Yeah. Now let's start from here once again. Let us start from this point once again. How to calculate the rest of the values. One thing I wanted to inform you, most of you were asking me of the clarity of the screen. The one thing that you need to do is you need to just click the right top corner three buttons in your on your screen, and you'll find something called as quality in that. Click on that quality and set it to 480p. It's the pixel resolution. Because you are on some other low level resolutions, the screen may not be clear for you. I request you all to do that. While you're watching on the video, just click on the right corner three buttons. You'll have some pop-up as report, quality, captions, playback, watch in VR, help and feedback. In that, click on the quality option, setting quality. So you can set different quality options, and because of that, there may not there is some difference of quality in that. So you'll get a better quality if you set it to 480p. I'm going to tell you what we have done. The first and second row of this RH criteria is always uh, completed by using the given characteristic equation, the coefficients of even and odd polynomial, and how to find the rest of the elements is by using the first two rows. And I'm going to tell you once again, this is EC minus AD by C. So in order to find this, you need to consider these as A, B, C, D. In order to find this, you need to consider these as A, B, C, and D again. This is what you have to do. So in the first case, it is 18 into 8 minus 16 into 1 by 8. It was 144 minus 16 by 8. It is 128 by 8, and that was already again 16. Hope that's correct. So this value is, what is this value enough? It is 16. Why not find this? What we have done, we have taken the second one, that is here now C is 8, B is 5. So 5 into 8 minus A is 1, and D you don't have anything, so it is 0 by 8. This will give you 5. So this element is second element in the third row is 5, and this is again a 0, or you can also make a 0 here. Now in order to find the next elements, just be careful. It's very important. In order to find the next coefficient of S1 element here, you need to consider this as A, this as B, this as C, and this as D. Now apply the same expression. You can apply the same expression as we have done. This is BC minus AD by C. If you apply BC minus AD by C again, what is BC? It is BC is 16 into 16 minus 8 into 5. So B is 16, C is 16. 16 into 16 minus AD, 8 into 5 by C. By C is 16 again. So 16 into 16 will give you 256 minus 8 fives are 40 by 16. So 256 minus 40 will give you 216 by 16. 216 by 16 will give you 13.5. So 16 into 16 minus 8 into 5, maybe numbers are correct. So 256 minus 40 is 216 divided by 16. So this will give you some 13.5 here. So that is how you'll find this row. And in order to find the next one, what you need to do, you need to take this B and D to the next column, these as B and D. Now because they are multiplied with zeros, 16 into 0 minus 8 into 0 by 16, this will give you a 0. So this is a 0. And when you are doing with the next one, find the next row elements. So you need to take the upper elements of that particular row and write them as this is A now, this is B, this is C, and this is D. In order to find this element, what you need to do, you need to take the same expressions BC minus AD by C, and if you do that, what would you get? B, value of B is 5 here. If you observe, this is 5, and C is 13.5 minus 16 into 0 by 13.5 will give you 5. So this is a 5, and here because you have a zeros, you'll get a 0 here. So after getting this, how to decide on the comment on the stability of the system, that I'll tell you now. Hope this is clear till now. Hope this filling the routes array is clear. So this we have done now. So this is routes array. Yeah, now this is routes array. You only have to look at first column element sign. Comment on stability. Route has told that in order to comment on the stability of the given system, if these are the conditions, if all first column elements are positive, all the first column elements are positive, I'm just telling you very slowly, and system is a stable system. This is very important. If first column elements are positive, then the system is a stable system. Now let's look at these first column elements. 1 is a positive element, 8 is positive, 16 is also here positive, 13.5 is also positive, 5 is also positive. Now we can say that this system is a stable system because in the routes array, the first fitting, the first column elements are all positive. First column elements are all positive. Mahesh Kusma, good evening, sir. Good evening. Advaita Goldie, thank you for the explanation, sir. Thank you. Advaita, good evening, sir. Good evening. Soumya, nice explanation, sir. Thank you. So, here the given system is a stable system. Here the given system is a stable system because all the first column elements in the routes array are positive elements. Now, when will it be unstable system? As we have told that if the first column elements are positive, that also implies that there are no negative elements, or we'll say in other words, no sign changes. So we can also state something like this: if there are no sign changes in first column of routes array, then system is a stable system. Then the system is a stable system. So this is the condition. There are no sign changes in the first column of routes array. The system is a stable system. Hope this is clear. I'll just once again go back and tell you what we have done. You will be given a characteristic equation like this. If an open loop transfer function is given, you need to take 1 plus g of s into h of s is equal to 0 and find this characteristic equation. And you will be asked to find the number of roots on the left half of S-plane or comment on the stability of the system. You need to prepare the routes array first. So in routes array, the first two columns are always, first two rows are always filled by using the given characteristic equation. If the highest polynomial is an even polynomial, consider coefficients of all even terms and write it in the first row. And in the second row, because we have already written the coefficients of even terms, you'll write the odd terms. Let us say if the first term is an odd coefficient, highest coefficient is the odd term. So you'll write the odd coefficients, then you'll write the even coefficient. So the first two rows will be filled from the routes given characteristic equation, and starting from the third one, you will consider the first two rows as A, B, C, D elements and apply BC minus AD by C. Then you will find the next row elements. Likewise, you'll complete this routes array, and if there are no sign changes in the first, if there are no sign changes in the given routes array, if there are no sign changes, then the system is said to be a stable system. And when the system is stable system, when all the roots are on the left half of S plane, because the given polynomial is of s power 4, so because it is s power 4, you'll have 4 roots. And question asked was, if you look at, find the number of roots on the left half of S plane and right half of S plane. So here the number of roots on left half of S plane are 4. Why? Because it is a stable system. Whenever it is a stable system and there are no sign changes, it is a stable system and all the roots will be on the left half of the S plane. And what is the number of roots on right half of S plane? Number of roots on right half of S plane are 0. There are no roots on the right half of the S plane. Hope this is clear for you. So what does this sign changes indicate? Let us take one. Let me tell you that. What I told you, if no sign changes where in first column of array, routes array, then all roots are on left half of S plane and the system is said to be a stable system. Lakshman, good evening, sir. Good evening, Lakshman. Now, what if there are sign changes? It will be one or two or three or sign changes. I'll also tell you what is that. Number of sign changes indicate the number of roots on right half of S plane. If there is some sign change, then it indicates that, sorry, let me tell you, if there are two sign changes. How many sign changes? If there are two sign changes, we can say that there are two roots on right half of S plane, and because we have four roots, we are taking the previous example. Because two roots are on right half of S plane, The rest of the two roots will be on left half of S plane. This is how you have to tell. So what does number of sign changes indicate? Number of sign changes indicate number of roots on the right half of S plane. Does not indicate number of roots on the left half of S plane. Number of sign changes will always indicate number of roots or poles on the right half of the S plane. And if there are no sign changes in the first column of routes array, then we say that all the roots are on the left half of S plane and the system is a stable system. And whenever you have this roots on the right half of S plane, because I have already explained you about this roots on the right half of S plane, whenever we have a root on the right half of S plane, we say that the system is an unstable system. Means what does number of sign changes indicate? If there are sign changes in the first column of routes array, we can say that it can be an unstable system. It can be an unstable system. So number of sign changes is very important in routes array. Let me tell you once again. We will complete the routes array. First two rows of routes array is filled with the coefficients of the given characteristic equation. If the characteristic equation is not given and an open loop transfer function is given, try to find the closed characteristic equation by using 1 plus g of s into h of s, and from the characteristic equation fill the first write the highest coefficient polynomial and fill the first two rows of the routes array with the coefficients of the even and odd terms in the characteristic equation, and find the rest of the elements in the routes array by using bc minus ad by c. And once you complete the routes array, check if there are any sign changes in the first column, and if there are some if there are no sign changes in the first column, we can say all the roots of the given characteristic equation are on the left half of the S plane and the system is a stable system. If at all there are sign changes in the given if there are sign changes in obtained routes array, the number of sign changes will indicate that the number as many number are on the right half of S plane, and the system can be an unstable or marginally stable system. If there are right side, completely unstable system. So let us also take one more example and let's see some other conditions. Let me take you this example, a bit big one. S power 6 plus 2s power 5 plus 8s power 4 plus 12s cube plus 20s square plus 16s 16 is equal to 0. So this is s power 6 plus 2s power 5 plus 8s power 4 plus 12s cube plus 20s square 16s plus 16 is equal to 0. Let us try to do this. What is that? First we need to do, write the highest power. It's an even power, so s power 6, s power 5, s power 4, s cube, s square, s power 1 and s power 0. Now s power 6 is the even polynomial, so you have a 1 here, and s power 4 you have an 8 here, s square you have a 20, and s power 0 you have 16. So we have to fill the first two rows. So s power 5 coefficient is 2 and s cube coefficient is 12, s power 1 coefficient is 16, and this is a 0. Now how to find this? I'm sorry. Let us take this as A, B, C and D. So what is BC? 8 into 2 minus AD 1 into 12 by C. So 8 to the 16 minus 12 by 2. It is 4 by 2 is giving you 2. So what is this element? It is 2. Now we need to shift this B and D. So let us take this as B and D enough. Now what is that value you need to find? So it is B into C minus, so this is B, right? It's B into C minus A into D, A into D by C. What is this? 20 2s are 40 minus 16 by 2. It is 24 by 2 is 12. We'll get a 12 here. And next we need to find B and T, shift it here. 40 minus 16 is 24. 24 by 2 is 12, right? So B and D are shifted again here. Now what is B into C? 16 into 2 minus A into D, 1 into 0 by 2, it is 16. This is again 16 here. And this you can leave it. Now when you are doing the next one, you need to cancel this and take this as A, this as B, this as C, and this as D. Now if you do this, what are we getting? We have to look at that. This is very interesting. This is one difficulty we face while doing Routh's array. Now when you do, what is it? BC minus AD by C, right? Is the value of B and C. See, B 12 to 12 into 2 minus A and D is also 12 into 2 by C is 2. What is this value you'll get? You'll get a 0. Just be careful, this is a 0 here. Also, if you shift this B and D, if this is B and this is D, what is that you'll get? So 16B into C minus A into D by value is again a 0. So this is again a 0. Obviously you'll get a 0. So there is a row of zeros. This is very important. A row of zeros. And we cannot find the next term. See, if you try to find the next term, let us try to find the next term, next row element. Let's try to find the next row element. What would be this element? What would that be element be? Now we'll cancel these terms and take this as A, this as C, this as B and D. What is BC? Is 12 into 0 minus AD 2 into 0 by 0. This is something 0 by 0 or inferior. This is not a valid form. So whenever you come across such situation where a row is becoming 0, what you have to do? And someone tell me what you have to do if you get a 0 row. Why there can't be a 0, or if there is a 0 we cannot find the rest of the elements. If we can't find the rest of the elements, we cannot say either it is a all the coefficients are positive or negative, or you cannot comment on the stability. It's a difficulty. In such cases, what you have to do is requesting you to just tell me if there is any possibility of doing this. I'll tell you the solution to this. You can do something like this. Whenever you have all zeros, it indicates the roots are on imaginary axis and it is an oscillatory system basically. So in such cases, we'll also discuss these things a little later, but what you have to do mathematically, or what you have to do whenever you have such all zeros case. I'll tell you in a separate page, then we'll come back and we'll try to solve. So this is one problem. What is that? We have got all zeros. All zeros. All zeros in a row of Routh's array. Then procedure is consider the row above all zeros row. You need to consider. You need to consider the row above all zeros row and write an auxiliary equation. Then differentiate it and write the coefficients. I'll slowly explain you what are these, but just remember what you need to do. You need to consider the all zeros row above the row above the all zeros row and write an auxiliary equation to this and differentiate it, then write the coefficients. This is what you have to do. Now let's go back to that. What you need to do, you need to consider the row above this row. So this is now because 1 was a coefficient of s power 6 and 8 was the coefficient of s power 4. Now if you observe, similarly this is the coefficient of s power 4 we can take, and this will be the, because this is an even number, this will be the coefficient of s square, this will be the coefficient of s power 0. Write an auxiliary equation a of s. A of s is equal to, what can I write? 2s power 4 plus 12s square plus 16 s power 0 is equal to 0. And you need to differentiate this auxiliary equation with respect to s. Once again I am repeating you, consider the row above all zeros row, and because this one was the coefficient of s power 6, we can take 2 as the coefficient of s power 4, although it is not exact coefficient of s power 4 here. You need to consider this 2 as the coefficient of s power 4, and this will be, this is s power 4 term, this is s square, because this being s power 6, this is s power 4, right? Similarly, if this is s power 4, this is s square, and this is s power 0. So 2s power 4 plus 12s square plus 16 equal to 0. Differentiate it. Differentiate it. 4 2s are 8 s cube plus 12 2s are 24s. Differentiation of a constant is a 0. So this will give you 8 s cube plus 24s. Now because we have s cube here, we have got the s cube coefficient. What is the coefficient of s cube here? S cube coefficient is 8. If this is s cube, what is this? This is s power 1. So you can replace this with the coefficient of s cube and s power 1. What is the coefficient of s cube? It is 8. Coefficient of s power 1 is 24. You can replace with this. You can complete the array now. We can complete the array. We'll try to remove all this and we'll try to complete this array. Hope this is clear for you. I'll also repeat this once again, don't worry. This is 16, this is 12, and this is 2. Now this is 8 and 24. How to find this again? Now coming back to our procedure. So you might have understood this auxiliary equation. Just trying to remove that and try to find again. So what is this A? This is B, this is C, and this is D. Now what is BC minus AD by C again? This B value 12 into C is 8 minus 24 into 2 by 8, right? So let's calculate this. I'll just take some calculator and try to find this. So 12 into 8 will give me 96 minus 24 2s are 48 by 8. So 96 minus 48 is 48. So 48 divided by 8. 48 divided by 8 will give me 6. This value is 6 now. This value is 6. Coefficient of s square is 6. What have we done? In s power 3, we got all zeros. So we have to this s power 4 row and try to get an auxiliary equation, differentiate it, and we have written the coefficients of that auxiliary equation, differentiated of auxiliary equation, and then we are writing this. Now let us shift this again. Now let us shift B and D. So this will be B and this will be D. So what is AD minus BC again? So let us try to find AD minus BC or BC minus AD. It's not AD minus BC, it's BC minus AD by C. E is 16, C is 8, minus A is 2, D is 0, by C is 8. So this will be a 16. So this is a 16 value. Now let us find the rest of the terms, and You need to find this term. It is 24 into 6 minus 8 into 16 by 6. This is one value. I want you to tell this value, and obviously this value, if you find, if by practice you can write it, it will be 60. So what is 24 into 6 minus, let us write 24 into 6, it is 144, minus 16 into 8 is 128 by 6. 144 minus 128 will give you 16 by 6. So he can write the value here. So it is 16 by 6. So this is also a positive value. Now you need to observe all the rows of first column elements of the routes array. Now this is a positive value, this is a positive value, this is also a positive value, 8 is a positive value, 6 is a positive value, this is also a positive value, this. Now from this, what you can write is very important. All first column elements are positive, but we have all zeros, which is an oscillatory system which can be marginally stable or unstable. How do you decide this? We have got all positive and we say actually it is a positive, but because we have all zeros we cannot say it is stable. Either it can be a marginally stable or an unstable system, and there are there is one condition. We have got an auxiliary equation, right? A of s is equal to, what is that? A of s is equal to, just will write this, 2s power 4 plus 12, 2s power 4 plus 12s square 16 is equal to 0. We can comment on the exact stability of the system, that it is marginally stable or unstable, only if we know roots of this. So we need to find the roots of this. Let's try to find them. I'll take s power 4. I'm taking 2 common. It is 2 6 12 s square plus 2 8. So you can write minus b plus or minus under root of b square minus 4ac by 2a. So that will give you minus 6 plus or minus under root of 8 8 are 64 minus 8 by 2 into 1. So what is that value that you get? Minus 6 plus or minus sorry, minus b value is 6, b square, 6 6 are 36. So it is 36 minus 4 into 8, 4ac, right? 4 into b square minus 4ac, 4 into a value is 1. This is ax square plus bx plus c. I'm taking s square as something like x, so it will give me s square. So it is minus, be more specific, I'll write here once again. We'll just take this auxiliary equation to the next slide, and I'll take that. Yeah, now I'll you as you require. You can also take it that way, but you can also write it this way, right? So it is 2s power 4 plus 12s square plus 16 is equal to 0. Plus 16 is equal to 0. If you take common 2, it is s power 4 plus 6s square plus 8 is equal to 0. Let s square is equal to x. Finally, you are practice to this, so I'm writing. So this is x square plus 16x plus 8 is equal to 0. This is in the form of ax square plus bx plus c is equal to 0, where the roots that you generally write are, roots are x1 comma x2 is equal to, x1 comma x2 is equal to minus b plus or minus under root of b square minus 4ac by 2a So this is what is x1 actually. If you write x1, this is s1. So s1 square comma s2 square is equal to minus b minus, not 16, it is 6, minus b plus or minus under root of b square. 6 6 are 36 minus 4 into a into c is 8 by 2 into 1. This is minus 6 plus or minus under root of 4 8s are 32. 32 minus 6, 34 by 2. This is minus 6 plus or minus 2 by 2. I'll take this to the next slide once again. Now you can write this as s1 square s2 square is equal to minus 6 plus 2 by 2 minus 6 minus 2 by 2. So s1 square is equal to minus 6 plus 2 by 2. S2 square is equal to minus 6 minus 2 by 2. So s1 square is equal to minus 4 by 2. S2 square is equal to minus 8 by 2. So it is 2 times, it is 4 times. So s1 square is equal to minus 2. S2 square is equal to minus 4. So s1 comma s1, two roots. S1 square, right? So this is s1 if you are trying to write full roots. So S1 it is plus or minus j root 2. S2 it is plus or minus j2. Here if you observe, so this is S1 and S1 dash, S2 and S2 dash roots. Because if you see, this is S power 4 coefficient, S power 4, so the roots must be equal to 4. And the given question if you see is S power 6, so total roots are 6. This point you need to remember. And here if you observe this part, there are roots on imaginary axis are not repeated. We can say that this is a marginally stable system, and you can ultimately write total roots were 6 on imaginary axis. You have 4 on left half of S plane because all the first column elements were positive. Therefore, system is marginally stable system because you don't have repeated roots on the imaginary axis. It is a marginally stable system. This point is clear. Once again, we'll look at what we have done. We were given a characteristic equation. We tried to solve this and fill the routes array. When we were trying to fill this routes array, one row has become completely zero. Whenever a row becomes completely zero, it means it is an oscillatory system or the roots are on the imaginary axis. In that case, whenever all the elements of a particular row are zeros, cannot further continue because we'll get some undefined values. So we need to consider the row just above that particular row and write an auxiliary equation of the row that is above all zeros row and differentiate it. Then you will get the coefficients of the all zero rows. Can replace the zeros of all zero rows with the coefficients of the differentiated auxiliary equation and continue to fill the routes array. But although if you get the first column elements as completely positive, we cannot say that the system is a marginally stable system or an unstable system. If you get negative, that means if any of this, if there are sign changes in the first column, we can say there is a root on the right half and based on the number of sign changes, and can say that is an unstable system. If all the first column elements of a routes array are positive and if there is a all zeros row, we need to find the roots, whether roots are repeated on the imaginary axis. See, we have considered the row above this and try to find an auxiliary equation and found the coefficients and written it here, and we found that all the first column elements were positive. In such case, you need to consider this auxiliary equation and find the roots of that auxiliary equation. We have found the roots of that auxiliary equation, and if they are not repeated roots, then the system is an marginally stable system. This is what we have found, and given characteristic equation has six roots or six poles, out of which we have found that in the previous case, if you see, they are on the imaginary axis. Four roots are on the imaginary axis and all the first column elements are positive. So out of six, four are on the imaginary axis, therefore the rest will be on the left half of the S plane, and the system is a marginally stable system. Hope this point is clear. This is the case when all the first column elements, yeah, all the rows in a routes array, all zeros in a row of a routes array. This is what was the problem with this routes array. This was the first problem. There can also be another one. Let's move on to the other one. This was the problem ultimately. This is what problem was, and we have found the solution for it. Considering an auxiliary equation, differentiating it, writing the coefficients and solving the routes array, then finding whether it's a marginally stable system or an unstable system. Now, if you consider the next example, let me take you to the next example. Let us consider one more example now. I'll write one more example, that is, let's say s power 5 uh, as s power 4 plus 2s cube plus 2s square plus es plus 5 is equal to 0. This is a given characteristic equation, let us say, and we are asked to comment on the stability of the system or find the roots on the left and right, find the number of roots on the left and right half of the system. If we are asked to find comment on stability and find the number of roots on left and right half of the S plane, how we are going to do this? We'll follow the same procedure and try to find it. Construct the routes array. Let's start it from here. So let us write what is the highest polynomial here, s power 5. So s power 5 is first written, then we'll write s power 4, then s cube, then s square, s power 1 and s power 0. So I think you have understood this problem clearly. Once you have understood this, it is very easy to solve this problem. Now let us look at this problem. So first what we'll do, we'll write the coefficient. The coefficient here is 1. Here the coefficient is 2. Because we are writing odd terms, consider the odd terms first. So 1, 2 and 3. These are the coefficients. 1, 2 and first row we are filled out. And the second, this is even, again even. It is 1, 2 and 5. It is 1, 2 and 5. This is 2, this is 5. Now how do you find this? We'll consider this as A, this as B, this as C and this as D. Now BC minus AD by C is what we'll write. BC is 2 into 1 minus 2 into 1 by 1 is again a 0. C is a 0 value. Now let's shift this B and D. Now this will be B and this will be D. Now apply the same procedure. B is 3 into 1 minus 5 into 1 by 1. So this is 3 minus 5 is minus 2. This is minus 2 and you don't have 0. Are all the elements in this 0 in this particular row? No. This was the case that we have studied earlier. There is a 0 and there is one non-zero element in that particular row. How to solve this? It's again a problem. There is an all zero elements in a row, we have solved by using by taking an auxiliary equation, by considering the row above this row, and that thing we have done. Now, whenever you come across such situation, is the other problem, second problem that we come across while solving or while filling the routes array. That is, problem is, if a row of routes array has a 0 in first column, and if any one of the other element in that row is a non-zero, that is what we have come, right? If first one is a 0 and any one of the other element is a non-zero, then what we have to do? Solution is, consider a positive number epsilon and complete array, and apply limit epsilon tends to 0 and comment on the stability. This is what we'll do generally. So if a row in routes array has a 0 in first column, and if any of one of the other element in that particular row is a non-zero element, then consider a positive number epsilon and complete the array, and then apply limit epsilon tends to 0 and comment on the stability of the given system. This is what we will do. Let's do that. Now this must be replaced by a positive number epsilon. Now let us try to find the coefficients. So what is this coefficient? Now this will be A, B, C and D. So what is BC minus AD now? Now let us write BC minus AD. So BC minus AD by C is, E is 2, C is epsilon, minus A into D, minus of minus, that will be plus 2, right, by epsilon. So this is 2 epsilon plus 2 by epsilon. Now this will be, because you don't have any term here, this will be B and D will be shifted here, E and D. So BC minus, sorry, again writing the same formula and trying to find this. What is B value? E is 5, C is epsilon, minus A is 1 and D is 0 by epsilon. So this will give me 5. Similarly, S power 1 coefficient. If you are trying to find S power 1 coefficient, it is BC minus AD by C. BC minus AD by C. Let's try to find that. Now you need to change this. So this will be A, this is B, this is C and this is D. So let's write that. What is B? Minus 2 into C, 2 epsilon plus 2 by epsilon, minus A, epsilon D is 5 by 2 epsilon plus 2 by epsilon. You need to simplify this. This will give you minus 4 epsilon minus 4 by epsilon minus 5 epsilon by 2 epsilon plus 2 by epsilon. Simplify this, you'll get minus 4 epsilon minus 4 minus 5 epsilon square by 2 epsilon plus 2. You need to write that is negative of 5 epsilon square minus plus 4 epsilon plus 4 by 2 epsilon plus 2. Then what would be the other element? We'll have a 0 and this will be a 5. Now for this you need to apply limits for both of these. One is, I'll just take it to the next slide. I'll just cut this part, and we need to apply limit to this. I've considered this part, so we need to apply limit to this. Now first limit would be, let's write it here, limit epsilon tends to 0 to epsilon plus 2 by epsilon. When you write epsilon here, because this is being a positive number, this will be a positive infinite. Let's take the limit epsilon tends to 0, 5 epsilon square minus of I plus 4 epsilon plus 4 by 2 epsilon plus 2. If you apply epsilon here, epsilon tends to 0, you'll get minus 4 by 2, because this is a 0, this is a 0, this is a 0, this is a 0. It is minus 4 by 2 will give you minus 2. So this term is minus 2, and this is a plus infinity, and this is an epsilon. Now if I write routes array once again with all these terms, let's write this only first column elements. I'll write 1 1 epsilon. I'll write only first column elements is uh, let's take s power 5, right? So let's write this. This is s power 5, s power 4, s cube, s square, s power 1, and s power 0. 1 1. See, you have written 1 because we are only concentrated on first column. So 1 1 epsilon. So 1 1 epsilon and s square coefficient. If you are looking at this, we have applied limit to this and we got positive infinity. And s power 1 coefficient, we have got minus 2, so it is a negative number. S power 0 was a 5. If you see, s power 0 was a 5. So this is a 5. Now let us try to find the number of sign changes. Now if you observe, this is positive, this is also positive, positive, positive. Here you have a negative and here you have a positive. So here if you observe the number of sign changes, there is no sign change here, plus to plus, plus to plus, no sign change, plus to plus, no sign change. Here you have one sign change. And here there is another sign change. So you have two sign changes. Total number of roots are 5. So therefore, this is the second problem we have got. So number of sign changes is equal to total roots is equal to 5. What does number of sign changes indicate? Is equal to number of roots on right half of S plane. Therefore, out of total roots, how many are on left half of S plane and how many are on right half of S plane? Left half and right half. We have decided what is left half. Left half, sorry, right half. Right half total you will have, total roots are 5. Of that right we have 2. Therefore, rest of the 3 are on the left half of S plane. Therefore, because the roots are on right half of S plane, we can say that the system is an unstable system. Given system is an unstable system. Let me tell you once again what we have done. Uh, we have encountered a problem that we have got a 0 in the first element and rest, and at least one of the other element was a non-zero. In such case, what we need to do is, we need to, if a row of an routes array has a 0 in first column and if any one of the other element in that row is a non-zero, consider a positive epsilon, complete the array and apply the limit and comment on the stability. So we have got such case here. We have got 0 here. We have replaced it by an epsilon and completed the routes array. Then we try to apply limit to all this. Because this is already considered to be a positive, you need not worry about it, because we have considered this as a epsilon as a positive integer, positive value, positive number. So you'll always take this as a positive. And we have applied the limit and got the value as minus infinite for this s square coefficient, and s power 4 s power 1 coefficient we have got minus 2. So we have again written all the first coefficients. We have written all the first column elements with these numbers that are already obtained and these limits. There we found that there is a sign change. There are two sign changes, one from positive to negative at s square to s1, and from s power 1 to s power 0 there is again a sign change. So there are two sign changes. Number of sign changes will indicate number of roots on the right half of s plane. So because there are two roots on the right half of the s plane and the total number of roots given are 5, if you observe the polynomial given is s power 5, so you'll have 5 roots. So out of that 5 we have 2 on the right half of s plane. Obviously the rest of the roots will be on the left half of the s plane. So 3 roots are on the left half of s plane and 2 roots are on the right half of the s plane. Because there are roots on the right half of the s plane, the system is an unstable system. So this is what is RH criteria. You'll also be asked about finding the K value, or are some other problems with this. Uh, we'll try to solve that in one of the other sessions. But now let me start root locus. This was all about problem 1 and 2 that we have obtained. And finally, I'll just like to conclude that in RH, number of sign changes indicate number of, there are the sign changes in first column, indicate number of roots on the right half of S plane. If all are positive in first column, is a stable system. If you have all zeros, consider the auxiliary equation, differentiate it and try to complete the array. If only first element 0, consider an epsilon as the number or an integer and try to complete the array and comment on the stability by applying the limit. This is what we have done enough. Now in the next slide we'll do what is root locus. Shall complete what is root locus of the given problem, or root locus is, it is a technique to find the stability, comment on the stability of a given system, and it is root locus is defined as a locus of closed loop poles Kanchan Chaudhary. Good evening, sir. Good evening. Mohammad Azhar Ahmad. Good evening, sir. Good evening. Kiran made simple and easy to understand, sir. Very nice. Thank you, sir. So, closed loop poles obtained when system in K is varied from 0 to infinity. So, this is the root locus. So, root locus is defined as a locus of closed loop poles obtained when the system gain is varied from 0 to infinity. So let us try to solve what are the, let us try to look at what are the different steps that are in root locus and how to solve a given question. One thing that you need to understand is we will consider the open loop transfer function. uh, Root locus obtained for an open loop transfer function. We need to draw a root locus for an open loop transfer function given. So for that there are some steps that need to be followed. I'll just write those steps first once, one by one. So root locus is symmetrical about real axis. This is the first point. Second one is, whenever you are given a question, you need to find number of poles and zeros and mark them as p is equal to and n z is equal to number. Third step that you need to do is location of poles and zeros. Where are they located? Right, p1, p2 and so on, and z1, z2 and so on. After this, we'll try to plot a pole zero plot. We'll try to plot pole zeros on S plane. Then after this, we'll find the root locus path on real axis. Whether a given point on the real axis is on root locus or not. Then we would find what is called as number of asymptotes. I'll tell you what are these number of asymptotes. Then we shall find angle of we'll find what is the angle of asymptotes. These are some of the steps. There are also so many other steps. First point is root locus is always symmetrical about the real axis, and the root locus is plotted on an S plane, and number of poles and zeros must be identified in the given transfer function, and also find the location of those poles and zeros and plot a pole zero plot. Pole zero, mark the pole zeros on the pole zero plot, and root locus path is to be identified on the real axis, whether the where does the root locus lie on the real axis. And then you need to find number of asymptotes. Number of asymptotes is just nothing but difference of p and z. Then you need to find the angle of asymptotes. You have an expression theta is equal to 2q plus 1 into 180 by p minus z. And once you find this, we are done with angle of asymptotes, and we'll draw them. We'll draw these asymptotes, and if there exist any take away or break in points, we will try to find them. This being a crash course, I'm just trying to give you a glimpse of everything, and we'll find this breakaway and break in points. There is a procedure to do that. We'll solve one problem. You may not come across all these steps in all the problems. There are some in some problems you may not come across breakaway and break in points. I'll tell you where you'll get this breakaway and break in points even. Santosh Rajavansi, yes sir ji, yes, good evening. So breakaway and break in points, we'll also find them breakaway and break in points, and we'll find what is the if at all there is some intersection of root locus with a omega axis. If at all root locus is intersecting or not, if it intersects, where does it intersect? That's what we will find it. So that is the intersection of root locus with j omega axis. And if you have complex conjugate poles and zeros, we will have to also find angle of arrival and angle of departure. Keeping in mind that I'm assuming that you already know these, some of you at least. If not, just try to remember these steps one by one, and you may not come across all these steps, but most of the cases you'll have these steps in common. In almost all the problems, these steps are common, and these will be only applicable to some questions, in which we require breakaway and break. If there are breakaway points, we'll try to find them. If there is intersection that needs to be that we feel we if we have some intersection of root locus with j omega, we'll try to find that intersection. And if there are complex conjugate poles and zeros, we'll try to find out angle of arrival and angle of departure. So before this start of this root locus, I would like to tell you some points once again. Root locus will always start at a pole and end at a zero. Root locus path will start at a pole and end at a zero. You always have to remember this. And poles need not be real always. Poles can be complex conjugate also. Every root locus path will start at a pole and end at a zero. This is very important point that you need to remember. Every root locus path will start at a pole and end at a zero. Keeping this in mind, we'll take up one problem and try to find is also magnitude and angle condition, which is very important. But we will try to take up one question and try to solve it, and I'll let you know. We'll take up one problem and I'll let you know if, yeah, let us take one problem. Example, I'm taking one problem from when T of s is equal to k by s, take a product, k by s into s plus 2. Let us say this is a given question and we are asked to plot root locus or find the stability of the system or find the value of k, the system to be stable using root locus. This is a question. So first one is, we always tell that root locus is symmetrical to real axis, and the second step what I told you was to find the number of poles and number of zeros. What are poles and zeros? Poles are the roots of the denominator and zeros are the roots of the numerator. Because there are no numerator values, roots, you have z is equal to 0 and p is equal to 2. So we need to find, because we have poles, we need to find the location. Because there are two poles, I'm trying to find p1 and p2 values. That is s into s plus 2 is equal to 0 denominator. So s is equal to 0 is one pole, s is equal to minus 2 is the other pole. So s is equal to one value is 0, other value is minus 2. So this is how you'll find the location of poles and zeros. So then I told you what are the different steps. So number of poles we have done, location of the poles. Next we need to plot it. Let's try to plot it. Let's try to plot this. Taking one. Let us try to plot it. I'll take the graph in the next session probably. For now, I'll just try to explain you on this. Yes, this is real axis. This is imaginary axis. Let us consider this as J1, J2, J3 positive, minus J1, minus J2, and minus J3. Let us term this as 1, 3, 4, 5. This as minus 1, minus 2, minus 3, minus 4, and minus 5. Now, here are the poles and zeros. You don't have zeros, right? You only have poles at 0 and minus 2. Pole is always, remember, pole is always represented by a cross mark and 0 by a circle or a 0. This is a pole and this is a 0. So we know that pole is represented by a cross and 0 by a circle or a 0. And you don't have any 0, so you not worry about it. And you have poles at 0 and minus 2. So there is a pole at this point and there is a pole at this point. So there are two poles. Now this is what is called as a pole 0 plot. Pole 0 We have done this pole 0 plot. Now just go back to the other point, pole 0 plot. Find the root locus path on the real axis. How to identify whether a point on root locus is a part, whether a point on the real axis is a part of root locus or not. This is very important. Uh, a point on real axis is said to be a part of root locus if to right of that point number of poles and zeros is odd. I'll tell you what is it. Let us take real axis, only real axis, points on real axis. Let me be here. Let you assume that you are standing here, and if you look towards your right, what is the number of poles and zeros? You don't have anything, so this point is not on the root locus. Till this point, if you observe, you are not. If you look to your right, and the total number of poles and zeros is 0, and when you come to just beside this point, or at least this -1, and if you see, the total number of poles and zeros to your right is 1. So this point, all these points are said to be on the root locus. Till this point, if you observe, till this point, if you are here, this is a root locus. After this, if you come to this point, what are the total number of poles and zeros? You need to count total poles and zeros. There are two poles. So two poles are said to be even. So this point is not on the real root locus. This is also not. This is also not. And any point that you take till infinity, negative infinity, is not a part of the root locus. So this is the root locus part. Hope this is clear for you. This is the root locus path on the root locus. The number of asymptotes. Now, how do you find the number of asymptotes? Let us take number of asymptotes. Number of asymptotes expression is number of asymptotes is p minus z. What is p value? Z is 0. So 2 means, as I told you, every root locus path will start at a pole, will start at this point and end at this point. So we have two poles and there are no zeros. So these two will end at some point. Should be some zero somewhere. So we will assume that the zeros are at the infinity, and we say that these poles are tending to this infinity, tending to these zeros which are at infinity. But because if we have the zeros exactly in the S plane, the location is known, we can directly find the path between them. But because they are at the infinity, we need some asymptote. Asymptotes are the straight lines in root locus which will guide the root locus path to tend to infinity. So number of asymptotes is always, let us say, if you have three poles and two zeros in a given question, one pole will end at the one zero, other pole will end at the other zero. Therefore, the third pole will not end at 0, it will end at a 0 which is at infinity. So this is p minus z. What is p in this case? P is 3. What is z? It is 2. So how many poles need the direction? Only one. P minus z, 3 minus this number of asymptotes is p minus z, 1. So this is how it is. It is always p minus z. So here you don't have any zeros, so both poles must be guided to tend to infinity. So it is. So let us see, we have known that we need to have two asymptotes, that is two straight lines. Where to draw these two asymptotes? That is one more question. That is also, we'll find one more thing, centroid in this uh, asymptote, and we have to draw straight lines. Where do we draw them? Do we draw them at -5, -4, -3, or 1 or 2, or on imaginary? Asymptotes are always drawn on the real axis. Where should we draw? We should draw them at centroid. What is centroid? Sigma is equal to sum of real part of poles minus sum of real part of zeros by p minus z. So this is a centroid expression. So we have real part of poles as minus 2 as 0 minus no zeros by poles minus 0 is 2. So it is a minus 1. Sum of real part of poles minus sum of real part of zeros pi. That means we need to draw straight lines at minus 1. So we need to draw straight line at minus 1. This is the centroid we have known. This centroid. How to draw that straight line? Do I need to draw it like this or like this or like this or like this? How do I need to draw them? Means there should also be some angle to draw them. That angle is angle of asymptotes. That is given as theta is equal to 2q plus 1 into 180 by q plus 1 into 180 by p minus z. If you find this, you need to substitute the values of q is equal to 0 and 1 because there are only two asymptotes. Q values will depend upon the number of asymptotes. If you have three asymptotes, you need to substitute q is equal to 0 once, 1 and 2. And if you substitute this, you'll get 90 degrees and 270 degrees. Means you need to draw two asymptotes with angles of 90 and 270 at minus 1. This is the conclusion. So we need to draw two asymptotes at minus 1, which is at minus 1 with an angle. One is 90 degrees, other one is 70 degrees. 70 degrees. So this is the number of asymptotes and their centroid and angle of asymptotes. Now we have two poles. As I told you, if you observe here, we have two poles and there is a root locus between them. Every root locus start at a pole and end at 0, but means we have two poles which are adjacent to each other. That means there should be a breakaway point. Here comes the breakaway point. If you don't have when do we get a breakaway point? Basically we get a breakaway point when two poles are adjacent to each other and there is a root locus between them. In some cases what happens is you'll have poles adjacent to each other and let's say you have a 0 here and a 0 here. Means there will be a root locus between them, that means they are tending to these zeros. In this case you don't have a breakaway point. Breakaway point will exist only if there are two poles adjacent to each other and there is a root locus between them, and only this root locus breakaway point will exist. So we need to find that breakaway point. How do you find that breakaway point is the question. So in order to find breakaway point, should consider 1 plus g of s into h of s in the given question and write k is equal to differentiate dk by ds and you will get the value of this. So let us take 1 plus g of s into h of s. That is you'll get s square plus 2s plus k is equal to 0. From this if you write k, it is minus s square minus 2s. If you differentiate and make it equal to 0, you'll get s is equal to minus 1. That means the breakaway point is same as is also a centroid and a breakaway point. So that means root locus is starting from this pole, and it is taking at this, and it is guided by this asymptote. So it will go along with this. It will go along with this on this actually, but I am representing it just aside. So this is the root locus path. Hope this concept is clear. So what have we done? Well, I'll just do a quick review of what we have done. We are given a question g of s, a by s into s plus 2 and asked to plot the root locus, or uh, we have taken RL as symmetrical to real axis always, and we have found number of poles and number of zeros and location of poles and zeros. And I told you every root locus path will start at a pole and end at a zero, and a point on real axis is said to be a part of the root locus if to the right of that point number of poles and zeros is a odd. So we try to do that, and next we try to find p minus z as number of asymptotes, and we cannot draw these straight lines wherever we want. We need to draw it at a particular point, that is centroid. Centroid is the point of intersection of the asymptotes. So that is sum of real part of poles minus sum of real part of zeros by p minus z. And we have tried to find what is angle of asymptotes as theta is equal to 2q plus 1 into 180 by p minus z. You need to substitute q value 0 if you have only one asymptote and find the angle. If you have two asymptotes, you need to take q is equal to 0 once and find and 1 second time and find these angles. And number of angles will depend upon number of asymptotes. If because we need angle for the asymptotes to be drawn at the centroid. So we have known the location of the asymptote, number of asymptotes, and the angle with which we need to draw. We have drawn them, and because there are two poles adjacent to each other and there is a root locus between them, we come across a breakaway point because every root locus must start at a pole and end at a zero. Zero is somewhere at infinity, so we need a breakaway point. In order to find the breakaway point, we consider 1 plus g of s into h of s. So you'll get s square plus 2s plus k equal to 0, and k is equal to minus s square minus 2s. Differentiate it and make it equal to 0, you'll get s is equal to 1. This is a breakaway point, and we need whether it is a valid breakaway point or not. If you look at the root locus path, it is between minus 2 and 0. So this was a minus 2 point and this is a 0, and the breakaway point is in between them, so breakaway is between them, so it is a valid breakaway point. Check whether it is a valid breakaway point or not. You can substitute this in k, and if k value is positive, it is a valid breakaway point. If it is an invalid, it's a negative value, it's an invalid breakaway point. So this was a valid breakaway point, and from there we have made the root locus travel along this asymptote. This red color, this represents asymptote, and this blue color represents the root locus path, and this is tending to 0, which is at infinity. Along with this asymptote, this is also tending to 0, which is at infinity. So this is one root locus path. You take this is one root locus path along with this, and this is the other root locus path which are breaking at -1, and the centroid is also equal to -1. Hope this is clear for you. So today we have discussed about stability concept, different f of s function, as well as with thought on s plane and stable, unstable, and everything. And we have tried to understand what is RH criteria. We come across two problems in that, 1 and 2. One was all zeros, and then we have seen what to do with that, and when there is only 0 at first element, and if there is other element as non-zero element, then we have seen what to do. In this case we have considered an auxiliary equation, and in this case we have considered an epsilon and try to solve and comment on the stability. Then we have taken what is root locus and try to comment on the stability of the system. If you take the root locus is on the left half of the s plane for any value of the k. You can say that system is stable system. So these are the takeaways from today's session. I hope this was a very informative session for all of you. Thank you all for joining me today for this 2 hours live session on control systems stability analysis using RH criteria and root locus. We'll also discuss root locus technique methods, and as Unacademy is India's #1 study channels, we have Theatrics, GATE, Electrical ECE and Instrumentation, Unacademy GATE, Unacademy GATE CE, Unacademy GATE Telugu, Unacademy SSC JE, Unacademy Computer Science, Unacademy GATE Questions, Electrical Junction, Unacademy Engineering Production Foundation, and Engineering Pathshala. So you can also join us on Telegram, https://t.me/creatrixgate electrical. You can use my code as YSK10 to get the maximum discount. Please do like and share and subscribe to this channel and also click on this bell icon to get more updates on Academy. Thank you all. Thank you so much for joining me today. Thank you.